So hello everyone, and welcome to the last session for the course. While your colleagues are streaming in, we are breaking new ground here. We are nearly 30 in this room, I think, so which is a good number. Thanks. Let me thank the people who have actually shown up with some regularity physically. Not because I don't want to thank the people who have been listening. Thanks to you as well, if you're listening right now, or if you will be listening later on. It's just that I think you can understand that it would be much more boring for me to talk to a completely empty room. Especially because we've been playing some kind of table tennis here, sort of asking questions to one another and try to answer them together. And even though I'm a bit schizophrenic, it would be much more difficult for me to do it alone. So now you may be wondering what we're going to do today, and we are going to have our second recap session for the course, which means that we are going to look back at some of the things we did when we were a little bit younger and inexperienced, at least as far as this course is concerned. You're still young and experienced. I'm old and, well, whatever I may be. That's not so important. Anyway, so the last time round, we were looking at recursive definitions in various forms for at least the two important classes of structures that we've been working with, lists and trees. And in fact, I do believe that by now, with all the exposure that you've had to these data structures in the data structures course, you have them tattooed on your forearms, so you don't even need your A4 cheat sheet for this exam in order to score points if you get any question on recursive definitions for those structures. What I was planning to do today was to look back at some of the linear algebra stuff to begin with. And of course, you may decide that this is not what you want to listen to. In this case, you just scream and you ask for something else. Okay, there are no screams yet in the room, and I cannot hear any screams from wherever you might be. So let's get started with some linear algebra. And let's look at something that we've been looking at since the very beginning, namely solving systems of linear equations. Now, some of the systems of linear equations that you've been working with throughout the semesters, they had some unspecified multiplying coefficients. So let's assume that I'm looking at a system like this, say. And I want to know where A, B, and C are real numbers. And I want to know for what values of A, B, and C this system has one solution, no solution, or infinitely many solutions. Okay, so you've been doing several exercises of this type. We've been looking at similar exercises in earlier course lectures, but sort of my spider senses tell me that even some people who are very good at this, they get scared when they see this A, B, and C instead of 1, 15, or 1,035,000,000. They probably would also get scared if they saw 1,035,000,000 as a multiplying coefficient, but then you will agree with me that A is actually much friendlier than a very, very long number. But the thing is that thou shalt not get scared. When you see something like this, you should just be happy. Why? Because this is an equation in two variables with two equations, a system of equations of two equations in two variables. That's a piece of cake. Why? Because you know how to do it. How do you solve a system of equations like this, regardless of the fact whether some of the coefficients are numbers that you know or numbers which we call A, B, and C, which in a program you would call a constant? So how do you solve this system of equations? Okay, you use the elementary row operations and the Gauss-Jordan method. So the first thing that you would do is to say, okay, let's turn this into an augmented matrix. And what is the augmented matrix that corresponds to this system of equations?
A1.
A1.
And 1,
1, 1 here. And here we write C and B, which are the two constant coefficients. Okay, so this is the augmented matrix. Oh, by the way, this guy has been eating too many Easter eggs. As people who solved one of the questions on Piazza that I posted realized, it can be really dangerous to eat too much of that. The expected weight gain is large. Okay, so what next? Comment, good start, but this is only the start. Now we want to use the elementary row operations to do something to this matrix. Namely, to put it into a form, at least in row echelon form, where we can immediately tell for what values of these parameters A, B, and C there is no solution, one solution, or infinitely many solutions. So what are these elementary row operations? And what would it be? I mean, what would be the first thing you would do to this matrix? You could swap the rows because we like ones. A could be any number whatsoever, so let's swap. Swaps. So we turn it into 1, 1. So these are ones, by the way. 1, 1, B, A, 1, C. So far, so good. Now that we have a 1 up here, we can try to do something below the 1. What is it that we want instead of the A there? We want a 0. Fantastic. So how do we get the 0 there? We subtract A times, or we multiply the first row by minus A, and we add it to the second row. So we perform this operation. We do minus A times the first row, and we add it to the second. Or in other words, we subtract A times the second row to the second, sorry. Okay, this leaves the first row unchanged. And now what happens to the second row? Okay, instead of the A, we get A plus minus A, so A minus A. We get our beloved 0 there. That's the thing we wanted. Then we have 1 minus A. And here we have, instead of the C, we have C minus A times B. Okay, so now we are in business. Now we can start working with this thing. Okay, so when is it that this system of equations that we brought into this reduced row echelon, this row echelon form matrix, augmented matrix, when is it that it won't have any solutions? Okay, so let's write this in red. When is it that there's going to be no solutions? Okay, so if A is 1, this 1 minus A becomes 0. So the last row will be 0, 0, and then something. This something will be So the last row becomes 0, 0. And then since A is 1, C minus B. Okay, so the algorithm tells us you will not have any solution. The system is inconsistent when what is true of C minus B? C minus B is not 0. So when C is different from B. Okay, so if A is 1 and C is different from B, then you have a row of the form 0, 0, something which is not 0. And that's when your spider senses immediately tell you no solution. Because this row will correspond to an equation 0 times x plus 0 times y equals something which is not 0. 0 equals something which is not 0. That's not possible. Okay, so if A is 1 and C is different from B, then there is no solution. Do we all agree with this? Okay, so next thing. Infinitely many solutions. When is it that you're going to get infinitely many solutions? Okay, so your colleague in the room is saying, well, I want the last row to be 0, 0, 0, all zeros. Because if the last row is all zeros, then really all I have is just one equation in two variables. The rank of the matrix is 1. This means that there is a free variable. When you have a free variable, you can instantiate it as you like, and then the value of the other variable will vary depending on what the value of the free variable is. So in this case, I want A equals to 1 and C equals to B. So what you have in that case is that the second row, the matrix, now I want to show it all at the same time. Okay, the matrix that we had at the end, in this case, becomes 1, 1, B, and then you have 0, 0, 0. This means that you have that x plus y should be equal to b. And this is a line with infinitely many points. You're defining all of the values of x and y which sum to b, whatever b will be, doesn't really matter, will give you solutions to the system of the original system of equations. So you have infinitely many of them. Okay, so in other words, to get infinitely many solutions, you want to have free variables. To have free variables, you want a rank which is smaller than the number of equations. So the number of variables that you have in your system. And in this case, this is when it happens. Are we happy with this? Okay, you know what I'm going to ask next. One solution. Okay, when do you think that you're going to get one solution here? And I think even though we like green, it's supposed to be spring at some point outside. Let me switch back to something which is more visible for everyone. Okay, when is it that we are going to get one solution? Okay, so your colleague here is saying when A is not 1. That's also logical because we've already examined all of the possible cases when A is 1. Okay, when A is not 1, that's absolutely right. So let's see what happens here at the thing that we had before. So when A is not 1, the matrix that we had would be something like this. 0, 1 minus A, and then C minus B, okay? When A is not 1, this quantity here is different from 0. So this means that actually we can put a 1 there by multiplying the second row by 1 over 1 minus A. Note, this is legal because 1 minus A is not 0. If 1 was equal to A, this would not be legal because you can't divide by 0. Yes?
Since A is not 1, shouldn't it be C minus AB?
C minus AB, absolutely. Absolutely. I had forgotten. Now. Oh, I'm moving the A. This should be an erasing thing, so let's erase. Yes. I was really enjoying moving the A around, but okay, so C minus AB. Splendid. Okay, so we can divide and we get a 1 here, and here we have C minus AB divided by 1 over A. Now this immediately tells us what the value of Y is. The value of Y is exactly this thing. And it's only one possible value, this one. Well, once we know the only possible value of Y, there is only one possible value of X, the one that we get by substituting the value of Y into the equation X plus Y equals B. So both the value of Y is unique, the value of X is unique. So there is only one solution. Any doubt whatsoever about what we did? Now, how many systems of linear equations have you solved so far? I would say far too many for your own good. Well, perhaps not far too many, I don't know. At a certain point, it can get pretty boring. But you see, that's not a big one. It's not a huge matrix. If you know how to solve a system of equations, you can solve that. The important thing here is that you know what really matters. Namely, how you go about solving the systems of equation. I use the elementary row operations, Luca. That's the answer. And second, you know when to figure out and how to figure out when that system of equation has no solution, one solution, infinitely many. No solution. You have a row of the form 0, 0, 0, 0 equal to something which is not 0. That's bullshit. You cannot solve that. Infinitely many solution, you want a free variable. So find the values of the coefficient that give you a free variable. One solution, well, you have a nice little system in which you have basically in the reduced form, the identity matrix or part of the matrix looks like the identity equals a certain number of values.
That last down there, the bottom left right corner.
Yes.
1 minus, I can't see what.
Oh, it's an A. It's our friend A. It's just that sort of the screen actually doesn't write particularly well down here. It's an A. It's the A by which we have divided. Use your Sherlock Holmes facilities to figure that out. But thanks for the question. The question was, what was this A? Oh, or what was that thing that I claim is an A? Or something of that kind, anyway. Okay, so far so good. So let's move on. How about linear transformations? Yeah, people are nodding their heads because linear transformation is something that we love. Or perhaps we don't love them, but it's something that belongs to a recap session. So suppose I have a function, and let's be concrete. Let's make it from pairs of real numbers to pairs of real numbers, vectors of dimension 2 to vectors of dimension 2. And actually, the dimensions could be arbitrary, from Rn to Rm. But let's be concrete. Now, when is such a transformation, when is such a function linear? Okay, one of your colleagues is saying when it maps the 0 vector to the 0 vector, where this big 0 is really a 0 vector of the, or in this case, of size 2. Well, actually, that's a consequence of linearity. It is true. Every linear function, every linear transformation will have this property. So if a transformation does not have this property, it's not linear. However, the definition of linearity is different. This is a consequence of the definition. The definition of linearity tells us how the transformation interacts with two key operations over vectors: summation of vectors and multiplication of a vector by a real number, what we call a scalar. So if I feed T with the sum of two vectors, which is a vector, what is the result going to be? No matter what the two vectors x1 and x2 are. Tx1 plus Tx2, as one of your colleagues is saying here. Absolutely. That's one of the two properties that the linear function must have. If the function you're staring at doesn't have this property, it is not linear. Because the passport of a linear function states two things. Thou shalt have this property, and in addition, it also tells you what is it that what is the result of applying T to C times a vector X. What is this? C times T of X. So that's property number 2, 2 check marks. So if somebody asks you, and it is, of course, it is true that these two properties actually imply this one. So it is true, actually, that T of 0 must be 0. Otherwise, T is not linear.
Should that not be the first thing we try somebody if we are finding out?
Okay, your colleague is saying, okay, shouldn't T of 0 equals 0 be the first thing we try if somebody asks us to argue that the function is not linear? Of course. However, a function might have that property and still not be linear, because not all functions that map 0 to 0 are linear. If it doesn't, it's not linear. But if it does, well, you cannot draw any conclusions. In that case, thou shalt try the other two. Okay, so let's look at an example. Suppose that I consider this transformation that takes a vector xy and maps it to the vector x squared 0. And I ask you, is this function linear? What would your answer be?
Doesn't actually apply any sort of multiplier to y. I mean,
Well, okay, your colleague is saying it doesn't do anything particularly interesting with y, but yeah, I mean, the function that maps every vector to the 0 vector is actually linear, even though it doesn't do anything particularly interesting to its input. It just ignores it and it spits out return 0, 0. Okay, your colleague in the room is saying, there is an x squared there. No matter how you think about linearity, it doesn't look like something that takes a square of a variable can be linear. I would be happier with 2x, she said. Okay, so, and in some sense, this is the right feeling. X squared is a parabola, if you think about it. It's not a line. It doesn't look like something which is linear. So let's put this understanding into on a formal footing. To show that this function is not linear, the only thing you need to do is to show that it fails either this property or this property. In fact, take your pick, it fails them both. So to argue that it fails these properties, or one of them, it's sufficient to find an example. So let's see. Can you give me an example, for instance, that shows that for some values of c, for some values of x, t times c of x is not c times t of x? You really need to just simply find some value of c and some vector x for which this property fails. That's all you need to do. In fact, in this specific case, I think you would be unlucky not to find some values that for which this is false. So give me some values, and then we calculate. So let's take c equals 2. It takes 2, baby. Okay, so let's take x equals don't take the 0 vector, please. Because note that this function actually maps the 0 vector to the 0 vector. Otherwise, we will be done already. Hmm? 3. And since actually the value of y doesn't matter, let's make it 0. Why not? It doesn't matter anyway. So let's keep it as simple as possible. Okay? So now all we need to do is to plug those values in. Let's see. What is t of 2 times 3, 0? Okay, it's t applied. Well, if I multiply all the entries in the value through in the vector 3, 0 by 2, what is it that I get? 6 here, because it's 2 times 3, and 0 here. And now, what is t of 6, 0? Well, 6 to the square is 6 times 6, 36, and I get a 0 here. Okay, so now let's see what happens if instead I take 2 times of 3, 0. Well, this is 2 times of multiplying what t of 3, 0 is 3 to the square is 9, and I 0 here. So I get 18, 0. Are the two vectors the same? Well, no, they are not. So, not linear. Well, I'm happy because the guy wanted it to be linear. In an exam situation, if I ask you, show that this function is not linear, and you get a result like this, you're happy because you got it. So you see, it's not mind-boggling. Once you know what it takes for a function to be linear, to show that a function is not linear, you just have to find an example that violates one of those properties. And typically, it's not difficult at all to find the example, because there are infinitely many examples that show that it doesn't work. I mean, if you pick one that where actually the equality that you want to falsify still holds, try another one. You've been unlucky. And typically, you don't need to look for large numbers. Keep the numbers as small as possible. Keep the vectors as simple as possible. If the simple one doesn't work, complicate it a little bit. There is no point in starting with something which is humongously complicated. Like I take my C to be 1,034,000,000 and my X to be large number over large number. You can try, but why should you? You know, I'm saying that because I've seen people being their worst enemies. They go for something complicated because it cannot be that simple. Why can't it be that simple? Typically, it is simple. So keep it simple. Remember the KISS method. I know I'm preaching a little bit, and I will keep doing that all the time because I'm doing it to myself anyway. I always forget these things. Sometimes what looks simple is actually simple. Not always.
Could you maybe briefly show how you display this with the summation?
Okay, so the question is, can we do something that has to do with the summation? So let's do it. Let's show that this function actually does not satisfy the property that the t applied to a sum of two vectors is the sum of t applied to the two vectors. Again, let's follow my lead. Let's keep the vectors as simple as possible. I'm not saying this will work. I'm just keeping it simple. Okay, so let's take t applied to the sum of the vectors 1, 0, 0, now I think I'm keeping it perhaps slightly too simple. So let's try this. Now, what is this? This is t applied to the vector 2, 0. Because I'm summing the coordinates point-wise, 1 plus 1 equals 2, 0 plus 0 equals 0. And now, if I apply t to this vector, I'm squaring the x component, and I'm mapping the second one to 0. On the other hand, if I compute the value of t applied to 1, 0 plus t applied to 1, 0, what is it that I'm going to get? Well, if I square 1, I get 1. So I get 1, 0 plus 1, 0. And I get 2, 0, which is not 4, 0.
If we would have done the original, the 1, 0 and the 0, 1.
Yeah, that was not a good. So if we would have done the thing I started, that's why I said that's too simple.
I also tried 2, 0 and 0, 2.
Yeah. But what? So the thing I had originally written would not have worked. That's why I erased it. I didn't even do the calculations because I realized straight away that it wouldn't work. But if it doesn't work, you will see immediately why it wouldn't work. Actually, the value of y does not matter in these examples because the map would send the second component to 0, regardless of what the value of y is. So intuitively, y is not the problem. It's x. It's the thing that it does to x, namely squaring it, which is the problem. You know, there is another way, which in fact does not require any guessing whatsoever of the counterexample to figure out whether the transformation is linear or not. Let's look at this other way. Since you're computer scientists, you don't want to guess. You want algorithms. So let's do an algorithm. Now, let me ask you, linear transformations are also related to transformations induced by an object that you love, namely matrices. Linear transformations are exactly the transformations that are induced by a matrix. We showed that. So a linear transformation must be induced by a matrix, and if it is linear, we know how to find the matrix. How do we find the matrix that would have induced this transformation that we've been working with, provided it were linear? So that's the transformation. Give me xy, I'll give you x squared 0. If this transformation were linear, it would be induced by what matrix? Okay, one of your colleagues is saying the identity matrix. So what would be the columns of this matrix? I mean, let's see whether it's the identity. So what would be the first column of this matrix? How would we find it out? We would apply T to what vector? To the first column of the identity matrix. And the second would be T applied to the second column of the identity matrix. So the identity matrix does play a role. So let's see what matrix comes out if we do it this way. Well, T of 1, 0, we've already seen what it is. It's 1, 0. T of 0, 1 is instead what vector? 0, 0. So what is the function that is induced by this matrix? Well, to figure that out, we multiply this matrix by xy. And the result would be the vector 0 down below here, and above x. Which is not what we wanted, would it? Because what we wanted was x squared 0. So this means that the transformation is not linear, because if it were linear, it would be induced by this matrix, and the matrix that we computed does not induce it. It induces a different transformation, which happens to be linear. And this brings us full circle to what your colleague suggested before. I would have liked to see a 2x there. Well, in this case, you don't get the 2x, but you would have got the 2x with this matrix here as your matrix inducing the transformation. Because if we do this multiplication, we get 2x here and 0 there. So if you don't want to guess values, just compute the matrix that would induce T if it were linear. If that matrix induces the transformation that you started from, then the transformation is linear. If it doesn't, Well, it's not. Okay, so we've seen many different ways of solving exercises of this type. Pick the one that you like best. And in fact, the last one involves absolutely no guessing whatsoever. You just turn the crank and compute, which is something that these machines do very well for us. And for these simple examples, we can do it too. For slightly larger ones, well, the machines do the work for us, because otherwise we make mistakes. At least I do. I don't know about you. Any question about linear transformations? How do you argue whether a transformation is linear or not? Yes?
Why do you select the matrix 1, 0, 0, 0?
Okay, the question is, why do you select the matrix 1, 0, 0, 0? Well, because the matrix that induces a linear transformation can be computed by applying the transformation to the columns of the identity matrix. So 1, 0 here is actually T of 1, 0, because T of 1, 0 is 1 square, 0, and 1 square is 1. 0, 0 is actually T of 0, 1. Why? Because you get 0 square, that's 0, and then a 0 as the y component. So no guessing whatsoever. Okay, so before we have a break, let me ask you another question related to linear transformations. I'll give you another transformation that says, give me an xy, I'll give you 2x, 3y plus 2x below here, and here I have a 1, 2x plus 1. Question, linear or not? Your colleague here in the front row, by the way, I should know your name, but I don't. Baldur, yeah. Your colleague Baldur is saying, absolutely not. In fact, he was the proponent before of a quick check. And the quick check is, well, first thing you do is plug the 0 vector in. If you don't get the 0 vector out, not linear. If you plug the 0 vector in, that is to say you compute T of 0, 0, what you get is 2 times 0 plus 1, 1, and then 0, which is 3 times 0 plus 2 times 0. So since this is not the 0 vector, T is not linear. In this case, no need to compute matrices, no need to guess vectors. You just use the property where you actually solve this exercise in 2 lines. First line that says, if T were linear, it should map the 0 vector to the 0 vector. T of 0 is not 0. Give me the points. Well, of course, you don't write, give me the points. I'll just give you the points. Because sweet and not sour. Even though we might be doing Chinese cooking here, which is good. But in this case, you don't want sour at the exam. You just want it sweet. So keep it sweet, keep it short, keep it simple. I'm getting hungry now. It's time for a break. And after the break, we will be doing a little bit more linear algebra on our way towards the exam.